In one shot, let me walk you through the entire journey of oil, from land drilling, offshore drilling, pipeline transport, refining, all the way to the gas station pump. And finally, the whole process of ending up inside your car's fuel tank. After watching this, you'll understand why we Americans are always racing around the world to secure oil. Oil extraction comes in two main forms: land drilling and offshore drilling. Let's start with a relatively easier method: land drilling. To extract oil, you first need to locate where it is. Scientists typically use satellites to conduct magnetic surveys. Where mineral deposits exist, the magnetic field gets disturbed. This creates what's called a magnetic anomaly zone. But this method only gives you a rough location. To accurately confirm whether oil is actually underground, the most widely used technique today is seismic surveying. This vehicle here is called a vibrosace truck. The heart of the vibrosace truck is this vibrator, which can weigh up to 11,000 pounds. When it touches the ground, it can continuously vibrate the earth and produce controllable seismic signals. Meanwhile, on the ground, there's also a seismic data collection truck. Workers place large numbers of geophones at designated spots. After the vibrosace truck sends out its signals, those vibrations reflect back when they hit different rock layers. Once the geophones on the surface pick up these reflected signals, they get analyzed. The system then maps out the corresponding geological structure to determine whether oil exists below. Once the presence of oil is confirmed, the next step is the actual extraction. Before drilling, workers first use a starter rig to bore a hole about 1.6 to 3.3 feet deep at the drilling site. Once that's done, the workers secure the hole. Then they can build the drilling platform. On top of the platform sits the derrick. The derrick connects through a drill pipe to a heavy-duty industrial drill bit. The drill bit is covered with cutting teeth made from materials like tungsten carbide or diamond. When the cutting teeth rotate, they can efficiently crush through rock. Here's a question: what actually drives the drill bit? Let's head up to the drilling platform where you'll see a rotary table here. The rotary table fits together with a hexagonal Kelly bar. The rotary table has gears that mesh with an adjacent gear driven by an engine. So when the drive wheel turns, the Kelly bar spins along with it. But this method creates way too much friction, so the Kelly bar typically doesn't make direct contact with the rotary table. Instead, a Kelly bushing is installed on the Kelly bar, with rollers inside it. This allows it to rotate while also smoothly moving up and down. At the bottom of the bushing is a locking mechanism. When it locks into the rotary table, it rotates together with it. This in turn drives the drill bit on the drill pipe to rotate. As the drill bit keeps spinning, it continuously bores deeper underground. Now here's a problem. When the drill bit grinds against rock, it generates massive amounts of heat. So to protect the drill bit, we have to cool it down. The solution is to use drilling mud. Workers pump drilling mud up to the top of the platform using high-pressure pumps on the ground. The drilling mud travels down through the hollow drill pipe all the way to the drill bit. This mud not only cools the bit, but also provides lubrication. As more mud gets pumped in, it rises back up along the well. The mud carries crushed rock fragments from the drill bit back to the surface. This helps clean out the well bore. After the mud is cleaned and the debris removed, it gets recycled and pumped back down into the well. But as the drilling depth increases, groundwater starts seeping into the well. This can cause the well bore to collapse. To solve this problem, workers first pull the drill bit out. Then they lower a casing pipe down into the well. There's a certain amount of space left between the casing and the rock wall. At this point, a lot of drilling mud still remains inside the well. So the device at the bottom of the casing has a check valve on it that prevents mud from flowing back into the casing. To push the mud out, workers drop a cement plug down into the well. Above the plug is cement, and below it is drilling mud. The cement plug then keeps pressing down, pushing the mud further down. The mud flows out through the check valve's outlet. The mud that escapes travels up along the gap between the casing and the rock wall. Once all the mud inside the well has been pushed out into that gap, then a second cement plug is used to press cement down until the two plugs meet up. The entire outer gap is now filled with cement. Once the cement hardens, it protects the well from collapsing. After that, the drill bit gets put back in and continues drilling deeper. Keep in mind that every time the drill reaches a certain depth, the process has to be repeated, inserting a new casing and then filling it with cement. So by the time we actually drill down to the oil-bearing zone, the well already has many layers of casing inside. As drilling continues, the bit eventually reaches the oil reservoir. Because oil is under enormous pressure, if we just kept drilling down, the results would be catastrophic. So at this point, a critically important piece of equipment must be installed on the surface: the blowout preventer. The blowout preventer can quickly seal the wellhead when pressure spikes, preventing oil and gas from blasting out uncontrolled. Once the blowout preventer is in place, drilling can continue. But sometimes, to handle complex geological conditions and achieve precise targeting, the drill needs to turn. So the drill bit gets swapped out for a mud motor. Inside the mud motor is a spiral-shaped rotor. When high-pressure mud flows through the rotor, it drives the drill bit to rotate. Also, at the joint of the mud motor, there's a small bend of 1 to 3 degrees. That small angle lets the drill bit control both its direction and tilt. This greatly improves the precision and accuracy of the drilling. Once the well is completely drilled, we move on to the final step of oil extraction. That's perforation. Workers first lower a perforating gun down to the extraction zone. Inside the perforating gun are shaped charges. When these charges detonate, the energy spreads outward and forms powerful jets. The jets instantly punch through the casing, cement ring, and a certain depth of rock formation. This creates perforation holes. The oil-bearing layer, originally blocked off by the casing and cement, now connects to the wellbore through these holes. Oil can then flow through those holes into the wellbore and be brought up to the surface. That's land-based oil drilling. So what about offshore drilling? The principle is pretty similar. First, you still have to do exploration. Once oil is detected, here's where offshore drilling differs from land drilling. Offshore drilling requires the construction of an offshore drilling platform. If the oil is located within about 1,640 feet below the water's surface, a fixed drilling platform is used directly. For deeper locations, a fixed platform is still used. But the fixed frame underneath has to be taller. If the depth reaches about 11,800 feet underwater, a fixed platform just isn't feasible anymore. At that point, we use a mobile drilling platform. The most commonly used type is this kind, the semi-submersible drilling platform. This platform is supported by two massive pontoons. These pontoons provide upward buoyancy for the drilling platform, and tugboats can tow the platform to different locations to operate. Some platforms even have propellers mounted at the bottom of the pontoons, which help adjust position and direction. 4 huge anchors connect to the pontoons, keeping the platform fixed in its designated area. Once everything is in place, water is continuously pumped into the pontoons to sink them below the sea surface. What's the benefit of doing this? Let's compare. On the right is a drilling platform whose pontoons aren't submerged below the surface. Under the force of waves, this platform rocks back and forth violently. But a platform with submerged pontoons stays remarkably stable. Now that we've covered what's underwater, let's look at what's above. In the center of the drilling platform is a lifting system used to raise and lower the drill bit. Around it are several cranes used to transfer supplies between the ships and the drilling platform. Since workers stay out at sea for up to a month at a time, there are living quarters here for eating and sleeping. Next to that is a helipad used to transport personnel and supplies. Below are the lifeboats, ready for evacuation in dangerous situations. These barrels store diesel, used to generate electricity, as well as fresh water for drinking. This is a flare boom. During oil extraction, flammable gases are also produced. These gases have to be separated and burned off through the flare boom to prevent explosions. Next, let's look at how oil is actually extracted from the seafloor. The principle is pretty similar to land drilling. Workers first operate the lifting system to lower the drill bit into this casing. Once it reaches the seabed, the drill bit starts working downward. The next steps are the same as land drilling. First, drilling mud is used to cool the drill bit. Then layer after layer of casing and cement is used to reinforce the well as it goes deeper. We won't go into detail again here. Once the drill reaches the oil reservoir, a blowout preventer is installed at the wellhead, just like on land. The principle of the blowout preventer is actually pretty simple. It uses an annular preventer and hydraulic ram blocks to control oil flow. The annular preventer at the top has a tightening mechanism. When tightened, it shuts off the oil channel, preventing a blowout. The hydraulic ram blocks below are used to control pressure. There's also a blind shear ram, which has a blade attached to it. If the well needs to be permanently sealed, the blade can slice straight through the pipe and form a complete seal. Once the oil passes through the blowout preventer's controls, it can flow steadily up from the seabed. Here's a question. How does the oil pulled up offshore actually get transported back to land? There are basically 2 ways. The first is, once the oil is extracted, it gets piped directly to land. The second method is that after extraction, the oil first goes through a production platform for initial processing. Then it gets transported to land once processing is complete. The actual subsea pipelines that move the oil aren't as simple as they look. The piping inside is extremely complex. Generally, after drilling is complete, the blowout preventer is removed. Then a Christmas tree is installed. The Christmas tree provides much better control and monitoring of oil flow, kind of like a smart faucet. Then, a jumper is connected to the Christmas tree. The jumper transports the oil from the Christmas tree to the production manifold. This in the middle is the production manifold, with a total of 6 Christmas trees connected to it. The production manifold is essentially a central hub. It can distribute oil into different output pipelines. For example, a PLET pipeline can only connect to one output pipeline, while a PLEM pipeline can connect to 2 pipelines at the same time. Between the output pipelines and the production manifold is also a booster pump. When the oil's flow rate and pressure aren't enough, the booster pump can quickly increase pressure and boost the oil flow. These output pipelines keep moving the oil, and then it travels upward through vertical pipes. Eventually, the oil reaches the production platform for initial processing. But all this equipment on the seafloor needs electricity to operate. So from the production platform, a large cable runs all the way down to the seabed. The cable first connects to this termination unit, then to the distribution unit next to it. Through this distribution unit, electricity gets sent out to each component along the pipeline, keeping everything running smoothly. Generally, there are multiple pipeline systems like this on the seafloor. They don't just connect to a single production platform, they can link to several. If the oil doesn't need initial processing, the pipelines can be run straight to onshore production facilities. But there's a problem here. After the production platform processes the oil, Each one would need its own dedicated pipeline to send the oil to onshore facilities. That would make pipeline installation extremely expensive. So the correct approach is to lay one shared pipeline. All the other pipelines connect to this shared one. Then the shared pipeline carries all the oil together to onshore production facilities. Besides connecting to land, another option is to transport the oil to a tanker ship out at sea and ship it from there. Here's another question. How do you actually install such complex piping underwater? That's where underwater robots come in. During installation, workers first use a crane to lower the Christmas tree to the seafloor. Then, with help from an underwater robot, the Christmas tree is precisely aligned with the wellhead. The next thing to install is the production manifold. After the crane lowers it, the underwater robot helps align the manifold's connector with the base platform. Once that's done, the same goes for the jumper. It gets lowered down, and the robot assists in connecting it to its target. The same process applies to all the other equipment connections. Once all the equipment is connected, the next step is to lay the pipelines. Before laying pipelines, engineers first scan and analyze the seabed. The seabed isn't flat, so they have to find a route that's relatively even and easy to lay pipe along. When they hit uneven terrain, they dig trenches to level out high spots. And when they hit dips or potholes, they fill them in with crushed rock. Once the route is smoothed out, the next step is laying the actual pipeline. There are 3 methods of laying pipeline. The first is towed installation for short pipelines, where the pipe is towed to the target location. Then it's lowered down to the seabed for connection. The other 2 methods are S-lay and J-lay. Let's focus on the S-lay method. A long pipeline is made by welding many shorter pipes together. Each pipe is about 40 feet long with a diameter of about 3 feet made of steel. The surface is also coated with reinforced concrete to add strength. 2 pipes are joined together and sealed using special materials to prevent oil leakage. This is a pipe laying vessel. The pipes are manufactured onshore. Then supply ships continuously deliver them out. Before being laid, each pipe section is welded together, then slowly lowered to the seabed. Once the pipeline starts being laid, the laying vessel must work nonstop until the job is done. Because if the vessel stays in one spot too long, waves or other forces could stretch and crack the pipeline, or even cause it to collapse. But the pipes don't always line up perfectly either. If there's any extra length, it gets cut off. Then they're welded together using mechanical connectors. During laying or use, the pipelines will inevitably get damaged, which means they have to be repaired. First, a crane is set up on the seabed. Then the damaged pipe section is lifted up. On the damaged pipe, isolation valves are installed, and holes are drilled into the pipe on both ends. Then, a bypass pipe is used to connect the 2 ends. Then, both isolation valves are closed, so oil can flow through the bypass pipe. Finally, 2 small lines are used to clean out any oil left in the damaged section. And just like that, the damaged section can be removed. Then a new pipe is put in and reconnected. Finally, the valves at both ends are opened and the bypass pipe is removed, and oil can flow through again. Besides subsea pipelines, as we mentioned earlier, oil can also be transported by tanker ship. This is a large oil tanker used to ship oil, over 390 feet long. Inside the tanker is actually one massive cargo hold. That huge hold is divided up into multiple smaller oil tanks. Since conditions out at sea can be brutal, ships often get tossed around violently. If the hold weren't divided, the oil inside would slosh back and forth from one side to the other. That would create enormous force against the hull. And once one side of the ship takes too much impact, the tanker could tip or capsize. So by dividing the tanker into many smaller compartments, when the oil moves, the force gets distributed across multiple small tanks. This design dramatically improves the ship's stability. You can clearly see the difference in the comparison. It's genius engineering. If we cut the tanker right in half, you can see that the hull is actually double layered. Why design it that way? Because if the tanker accidentally hits another vessel, the double layer design protects the oil inside the tanks much better. A single hulled ship is much more vulnerable to fracturing when struck. That could cause oil to spill into the ocean. Besides protecting the oil, the double layer design also serves as ballast. Because when the tanker isn't carrying any oil, it doesn't have enough weight to counter buoyancy, and it gets tossed around by the waves, which is really unsafe. The fix is simple. We just fill the space between the double layers with seawater. With added weight, the tanker stabilizes. When it's time to load oil into the cargo hold, we just pump the seawater out from between the layers. But the seawater that gets pumped into the ship may contain microbes or bacteria. Before discharging the seawater, it must be treated through this purification system before being released back into the ocean. This prevents invasive microbes from entering different sea regions. Here's a question. How do you actually load hundreds of thousands of tons of oil into the tanks? There's an important factor to consider here. The tanker's center of gravity. If the weight is distributed unevenly, the tanker could become too heavy on one side and capsize. So how do we solve this? There's actually a piping system above the tanks. When loading oil, the first pipeline is used to fill these 5 yellow tanks. Then a second pipeline fills the 5 purple tanks. Finally, a third pipeline fills the remaining 5 green tanks. With this design, no matter which pipeline is used to load or unload oil, the tanker's center of gravity always stays evenly distributed. And finally, the tanker delivers the oil to land. Now we know how oil is extracted and transported to land. Next, let's look at how this oil actually gets refined. The logic behind oil refining is actually pretty simple. Crude oil contains all sorts of organic compounds. We just need to find a way to separate these different compounds. And that's basically what refining is. But how do we actually separate them? In reality, oil refining is done using something called a distillation tower. Each level inside the distillation tower has a different temperature, with the temperature decreasing from bottom to top. During refining, crude oil is first sent into a furnace, where most of it gets vaporized. Then the vaporized gas, along with a small amount of liquid, gets sent down to the bottom of the distillation tower. At this point, their temperature is about 750 degrees Fahrenheit. The liquid settles at the bottom of the tower, while the hot gas rises up to the first tray. The tray design is really clever. Besides holding liquid, it also has individual bubble caps on it. As the gas rises, it can only pass through the bubble caps. After that, the gas enters the liquid sitting on the tray. If the liquid is at about 700 degrees Fahrenheit, and one component in the gas has a boiling point of about 707 degrees, then that gas instantly condenses, staying behind in the liquid on that tray. Of course, all gases with boiling points between 700 and 750 degrees Fahrenheit will also condense, while gases with boiling points below 700 degrees Fahrenheit will escape from the tray liquid and rise up to the second tray. If that tray's liquid is at about 570 degrees Fahrenheit, then any gas with boiling points between 570 and 707 degrees Fahrenheit will condense at this level, and so on, separating out level by level. The oil ends up split into many different products. As you can see, these products have made their way into nearly every corner of modern society. That's why oil is also called the lifeblood of industry. But here's a problem. The refining process isn't as flawless as it sounds. For instance, at the first tray, all gases with boiling points above 700 degrees Fahrenheit should condense here. But some gas components don't play by the rules. They illegally migrate up to the next tray and condense there instead. This obviously defeats the purpose of refining. The solution is actually pretty simple. Just route the condensed liquid from the upper tray back down to the level below through a pipe. Since the lower tray is hotter, it can re-vaporize that liquid. That way, only the desired components stay behind. Once the oil separation is done, what do we do with the leftover residue at the bottom? Actually, that residue still contains a lot of useful components, but these components have very high boiling points, some over 1,830 degrees Fahrenheit. How do we deal with that? Let's look at another experiment. Here's a container of water. Under standard atmospheric pressure, water boils at 212 degrees Fahrenheit. But if we lower the pressure inside the container, water might boil at just 122 degrees Fahrenheit. Based on this principle, the oil residue gets sent into a vacuum distillation unit. After distillation, the lighter components are turned into wax or lubricating oil, while the heavier components at the bottom become asphalt or industrial fuel. Keep in mind that many of the products from oil distillation require secondary processing. Take the most common product, gasoline. When it comes out of the distillation tower, it's called straight-run gasoline. Straight-run gasoline has a relatively low octane rating, usually between 40 and 60. When you hear numbers like 92 or 95, those refer to the gasoline's octane rating. The higher the octane number, the better the gasoline resists engine knocking. That's why modern gasoline typically requires an octane rating of at least 90. To produce higher octane gasoline, refineries typically use a process called catalytic reforming. This rearranges the molecular structure of the gasoline, producing gasoline components with higher octane ratings. But this gasoline still contains harmful components like sulfur compounds, which can't just be released as is. So it also needs to go through hydrotreating. The gasoline gets heated up and contacts a special catalyst to trigger a chemical reaction. This removes harmful components like sulfur compounds. Finally, gasoline blends from different sources are mixed at specific ratios with anti-knock additives and antioxidants added in. Only then do we get the finished gasoline that's ready to use. The refinery then stores the processed gasoline or ships it to regional fuel depots. From there, tanker trucks deliver the gasoline to gas stations that need it. Beneath every gas station are usually several massive underground storage tanks. Each tank holds about 8,000 gallons. But because these tanks stay buried underground for years, over time, they can start to corrode, which leads to gasoline leaks. That's why modern storage tanks have an outer shell made of fiberglass reinforced material. But here's another problem. Gasoline evaporates. Those vapors collect at the top of the storage tank. If the gasoline delivered by the tanker truck were just pumped directly into the storage tank, the vapors built up inside the tank would get pushed out into the atmosphere, creating a massive fire hazard. To solve this, when the tanker truck delivers gasoline, it first connects to a valve on the surface. When the tank is about 95% full, this flap valve here lifts up, sealing off the inlet to prevent overfilling. There's also another valve next to it, also connected to a pipe. When the left valve starts pumping in gas, as the oil level rises, the vapors collected inside the storage tank get pushed out through the valve on the right and sent back to the tanker truck. Those vapors are then returned to the processing plant. There, they get cooled back down, turning back into gasoline that's ready to use again. When we pull up and pump gas, the pump at the bottom of the underground tank gets activated. Then, through a long pipe, the gasoline travels up to the fuel nozzle. And just like that, our cars get fueled up.